Chapter 2, Matter and Minerals. Minerals are the building blocks of rocks. By definition, a mineral is naturally occurring, an inorganic solid, it's an ordered molecular structure, a definite chemical composition. In contrast, a rock is a solid aggregate of minerals. So here's an example where granite, which is a rock, and you can see with its large crystal sizes that it's made of several different minerals. For here, this quartz represents the gray semi-translucent crystals, hornblende represents the black opaque minerals, and feldspar the pink crystals in this granite. Composition of minerals. Elements are the basic building blocks of minerals. Less than 100 are known, 92 of them are naturally occurring. Atoms are the smallest particles of matter, which retain all the characteristics of an element. The atomic structure. The central region is called the nucleus, which consists of protons, which are positively charged, and neutrons, which are negatively charged. Then around the nucleus, you'll find electrons. These are negatively charged particles that surround the nucleus. They're located in discrete energy levels called shells. Okay? The periodic table is kind of like a catalog of elements. And in each one of these boxes, you'll find the name of the element, in this case helium, its atomic weight, which is the weight of its neutrons and protons added together, its symbol, which would be 1 or 2 letters, and atomic number, or the number of protons. You'll find, for example, that helium is a very light mineral, like 4, versus, let's say, calcium, which is 40. Okay? So these elements have different weights to them. It's important to know. The structure of atom. In the nucleus, we have protons and neutrons, and then we have these electrons orbiting in their different shells. The atomic number is the number of protons in an atom's nucleus. Now, how do these atoms bond together? They need to bond together to form various compounds with 2 or more other elements. Ions are atoms that gain or lose electrons. Okay, so you'll have these compounds of 2 or more elements, then you might have these ions of single elements floating around. Isotopes. Isotopes have a varying number of neutrons. So isotopes have different mass numbers because mass numbers are the sum of the neutrons and the protons. So if an isotope has a different number of neutrons, it's going to change an element's mass. Many isotopes are radioactive and emit energy and particles. Now, chemical bonding, the formation of a compound by combining 2 or more elements. Ionic bonding, atoms gain or lose the outermost valence electrons to form ions. The ionic compounds consist of an orderly arrangement of oppositely charged ions. Okay, this is the weakest form of bonding. For example, halite, NaCl. It's a good example here with this the chloride ion. It's missing as a spot left where it needs an electron, because here it only has 7, and it wants to have 8. So the sodium is going to loan it its extra electron there, and it's going to form a compound that's positive on one side and negative on the other side. Covalent bonds. Atoms share electrons to achieve electrical neutrality. These are generally stronger bonds than the ionic bonds. Both ionic covalent bonds typically occur in the same compound. So in this covalent bond between 2 hydrogen atoms, as they get closer together, the electrons are going to start seeking each other out until they form a unified cloud where this hydrogen molecule, the hydrogen is sharing the electrons amongst the nuclei there. Other types of bonding. Metallic bonding, the valence electrons are free to migrate amongst the atoms. It's weaker and less common than other bonds. It's metallic because as long as the electrons are free to migrate, that element is going to want to be able to, you can bend it, like taking a piece of copper, you can hammer it out into a sheet, you can pull it into a wire. It's metallic bonding. Isotopes and radioactive decay. The mass number is the sum of the protons and the neutrons in an atom. An isotope is an atom that exhibits variation in its mass number. Unstable isotopes emit particles and energy in a process known as radioactive decay. Now the structure of the minerals. Minerals consist of an orderly array of atoms chemically bonded to form a particular crystalline structure. The internal atomic arrangement in ionic compounds is determined by its ionic size. So, in some cases we have polymorphs. These are minerals with the same composition but different crystalline structures. For example, diamond and graphite. They're both just made out of carbon. Okay? Now, phase changes when one polymorph changes into another. In the case of diamond and graphite, here you see in the graphite, the carbon ions are forming these sheet structures with covalent bonds that are loosely bonded to each other with ionic bonds. The diamond, on the other hand, the carbon ions are bonding with as many other carbon ions as they can reach, forming a massive structure which is very strong. Graphite's one of the weakest minerals, and diamond's one of their strongest minerals. Okay, now in the field, we're actually able to identify many minerals based on physical properties that we can observe and test without any special tools. These are the primary diagnostic properties. These are determined by observation or performing a simple test. Several physical properties are used to identify hand samples of minerals. Okay, one is the crystal form, the external expression of the mineral's internal structure. This is often interrupted due to competition for space and rapid loss of heat. So not all crystals are going to be perfect. Some are going to be truncated, some are going to be slightly misshapen. Here's an example of crystals of pyrite. Now pyrite is often has this cubic crystal form, and other times it may form these almost dodecahedron-like crystals. Luster is the appearance of a mineral in reflected light. So how does that mineral reflect light? There are two basic categories, metallic and non-metallic. Other descriptive terms we may use are vitreous for glassy, sometimes they're silky, or sometimes earthy. Here is galena showing a metallic luster, and over here we see a mineral showing submetallic luster, which is in between metallic and earthy. Color. Color is generally unreliable for mineral identification. It's often highly variable due to slight changes in mineral chemistry, or sometimes the mineral has been weathered, so on the outside it has formed a different color. Exotic colorations of certain minerals are produced by produce gemstones. Quartz, for example, we may find in many different colors. That's from trace minerals that are, I guess, contaminating the quartz, so to speak, so that shows different colors. Streak. Streak is the color of a mineral in its powdered form. We scratch a mineral along a streak plate, which is a ceramic tile, and it may leave powder behind, and we can tell what color that is, and that's its streak. Hardness is resistance of a mineral to abrasion or scratching. All minerals are compared to a standard scale we call the Mohs hardness scale. So here's an example of streak. So here we have this unglazed porcelain tile or streak plate and a chunk of pyrite. So we scratch that pyrite on a streak plate. It'll leave this gray powdered streak behind. So that's the streak color of pyrite. Now Mohs hardness scale. It's not a very linear scale. It starts very weak and goes up till it rapidly jumps to diamond. Diamond's the strongest mineral. It's 10 on the Mohs hardness scale. The next one down is corundum, which is much weaker, and that's a 9. And there's topaz, and quartz is 7. Then we're down to fluorites of 4, gypsum and talc are 2 and 1. Now in the field, if you had a clear mineral and you couldn't really tell, clear white mineral, and weren't sure if it was calcite or fluorite or quartz, well, you can figure this out by hardness. If you can't scratch it with your fingernail, well, it's harder than a 2.5, but if a copper penny can scratch it, its hardness is going to be 3. So that might be calcite. If that mineral shows the other properties of calcite, that is, though. It might be fluorite if the copper penny can't scratch it, but a wire nail can. Now, if that clear mineral can scratch a glass plate or a streak plate, well, that's going to be a 7, and that's going to be quartz. Okay. Cleavage. Cleavage is a tendency to break along planes of weak bonding. So where we have those ionic bonds, minerals tend to break along those bond lines, forming flat, shiny surfaces. And these flat, shiny surfaces result in new geometric shapes. They're different than their crystal structure. And we talk about these by counting the number of planes in the crystal and the angles between adjacent planes. let's say you had a six-sided die, and between the top and the bottom of the die, you can pass a plane through there. That's one plane. Between the front and back, another plane. Those two would be at 90 degrees of each other. And then between the left and right sides, you can pass another plane, and that will be at 90 degrees from the other planes. That's cubic cleavage. So here's a diagram, and I was just talking about this cubic cleavage. In case this halite. So you can pass a plane between the front and the back, this blue plane. Between the top and the bottom is this yellow plane. Between the left and the right side is this pink plane. And these are three planes at 90 degrees, or cubic cleavage. The micas we'll talk about a lot has one plane of cleavage, and you could basically peel these minerals apart in sheets. Okay. Another example is calcite is 3 planes of cleavage at 90 degrees. It's rhobohedron cleavage. And then feldspar has 2 planes of cleavage at 90 degrees. Cleavage of muscovite mica. We see up here we have our sheets of silicon oxygen tetrahedra, which we'll talk about in a minute. This sheet is formed of covalent bonds, and it's ionically bonded to its sheet below it. So you can easily peel it apart with a fingernail or a knife blade. Now, fracture is the absence of cleavage when a mineral is broken. So some minerals don't have cleavage, and they'll just break apart with a rough surface, or they might break with circular indentations called conchoidal fractures. Another property is specific gravity. Each mineral has a weight you kind of expect to it. So the weight of the mineral divided by the weight of an equal volume of water gives us a ratio, so we can compare how heavy that mineral is compared to water, and the average value is 2.7. Okay. Here's a picture of conchoidal fracture. You see these kind of roundish marks. It's kind of like breaking a thick piece of glass. You might get conchoidal fractures at places of impact. Okay, now other properties. These are the special properties. These are special things that you can identify a mineral with, like magnetism. Magnetite is magnetic. Reaction to hydrochloric acid. Well, it's calcite. When we drop hydrochloric acid, will form carbon dioxide bubbles and fizz. Malleability. A chunk of native copper, you can warm it up and hammer it out. Taste. Halite, which is table salt, tastes salty. Smell. Sulfur smells like rotten eggs. Some minerals are elasticity. You can bend them and they'll bounce back, kind of like the micas again. You should be able to bend them and they'll bounce back in shape. And then there's double refraction, like calcite, because it's 3 planes of cleavage not at 90 degrees. That means this top surface and the bottom surface are not directly over each other. So when you're looking at the light coming through, the light's going to be refracted or bended by the bottom face, and then that light's going to be bent again by the top face. So it's going to make you look like you're seeing double, or double refraction. Okay, when it comes to mineral groups, there are nearly 4,000 minerals that have been named. We're going to focus on the rock-forming minerals. These are common minerals that make up most of the rocks of the Earth's crust. There are only a few dozen members. They're composed mainly of 8 elements that make up more than 98% of the continental crust. Oxygen is 46.6% of the continental crust. Silicon's 27.7%. Aluminum is 8.1%. Then we have potassium at 2.6%, and sodium at 2.8%, calcium at 3.6%, magnesium at 2.1%, iron at 5%. All the rest of the elements are just in 1.5% of the continental crust. So most of the minerals you'll expect to find oxygen and silicon, and a smattering of some of these maybe. So the most important mineral group is called the silicates. These comprise most of the rock-forming minerals, and very abundant to the large percentage of silicon and oxygen in the Earth's crust. The silicon and oxygen form silicon-oxygen tetrahedra. This is the fundamental building block for the silicates. 4 oxygen ions surround a much smaller silicon ion. Okay, and they form these tetrahedra that look like this. This is just one that's expanded out, so you can see that silicon is in the middle. It has a +4 positive charge to it. So each one of these oxygen ions are attracted to that +4 because they have -2 charges. Okay, so each one of these oxygens are sharing an electron, so it evens out this +4 charge with 1 electron from each one of these, so it leaves a molecule with a -4 charge. Joining silicate structures. Single tetrahedra link together to form various structures, and these will affect the crystal structure of minerals. And these structures are the isolated tetrahedra, ring structures, single and double chain structures, sheet or layer structures, and complex three-dimensional structures. Okay, so the independent tetrahedra, those independent tetrahedra, they may get bonded loosely with magnesium or iron ions. Single chain, the tetrahedra connect at oxygen on either side, forming a narrow chain. Double chain, two single chains form together, forming a little bit of a ring structure here. Now sheet structure, they'll just form like multiple double chains to form a sheet. And here's a 3D complex framework where the tetrahedra are trying to join as many other tetrahedras as they can at their 4 corners. Okay, so here are example minerals: olivine, which is magnesium and iron SiO4. Okay, has no cleavage. Okay, and here's an example of one of the crystals. These olivine makes very small rounded crystals. The peroxine group made of augite. Okay, have 2 planes at right angles. A single chain form. You see this planes of cleavage here, 90 degrees. And the amphibole group, or hornblende, takes basically magnesium, iron, and the silicon tetrahedra, but adds calcium into the mix and a little bit of water, and forms hornblende, which forms these double chains. And because this double chain is wider than a single chain, you'll get 2 planes of cleavage still, but they'll be at 60 and 120 degrees. Okay, the sheet structure, biotite and muscovite. Now, biotite is a dark silicate, we'll learn, and muscovite is a light silicate, and they form these sheets and have 1 plane of cleavage, and you can peel them apart. The complex three-dimensional network, well, we'll find our potassium feldspar, which has 2 planes of cleavage 90 degrees, and our quartz has that, but has no cleavage. Okay, so common silicate minerals. So we're going to break them up into light silicates and dark silicates. In this case, the light silicates, we have the feldspar group, which is the most common mineral group. They exhibit 2 directions of perfect cleavage at 90 degrees. Orthoclase is potassium feldspar, and plagioclase is a sodium-calcium feldspar, and they're the 2 most common members of the feldspar group. You can sometimes tell plagioclase feldspar apart from orthoclase, but sometimes on its crystal faces you might see some lines, which geologists call striations. Okay, another light silicate group that's very common is quartz, the only common silicate composed entirely of oxygen and silicon. Hard and resistant to weathering, has conchoidal fracture, often forms hexagonal crystals. And another one is muscovite, which we've seen already. It's the most common member of the mica family. Excellent cleavage in one direction, such that we can peel it apart into sheets. This produces the glimmering brilliance often seen in beach sand. Okay, here's a picture of muscovite, which is a light silicate. We'll get back to biotite. It's actually one of the dark silicates. One of the light silicates is clay minerals. Clay is a general term used to describe a variety of complex minerals. They exhibit a sheet or layered structure. Most are products of chemical weathering. Feldspars get weathered down and form new minerals called clay minerals. Now the dark silicates, first we have the olivine group. These are high temperature iron and magnesium silicates. Individual tetrahedra are linked together by iron and magnesium ions. They form small round crystals with no cleavage. So here's a little graphic showing the individual tetrahedra. They're loosely bonded together by magnesium or iron ions. The peroxine group, single chain structures involving iron and magnesium, 2 distinct cleavages at nearly 90 degrees. Augite is the most common mineral in the peroxine group. Amphibole group, double chain structures involving a variety of ions, 2 perfect cleavages, actually close to 120 and 60 degrees. Hornblende is the most common mineral in the amphibole group. Okay, here's a diagram of this where we have the augite is a single chain tetrahedra. So that forms a more compact crystal that allows for a 90 degrees angle between the planes of cleavage, where hornblende has a double chain, so that makes a wider crystal that causes it to have a larger angle between planes and a smaller angle than 90 degrees. So you end up with the 120 and the 60. They're important non-silicate minerals. So if you're not silicate, you're a non-silicate. Typically divided into classes based on anions. They comprise only 8% of Earth's crust, often occur as constituents in sedimentary rocks. So these non-silicate major groups are oxides, sulfides, carbonates, halides, and native elements. Here's a chart that goes through and talks about these major groups of non-silicates and names some major minerals. And the carbonates, you might have heard calcite. Okay, it's used in making cement. Halides, like halite, which is table salt. Okay, and sylvite, which is used in fertilizer. Oxides have hematite and magnetite, which are ores of iron. Corundum is a gemstone or abrasive. Ice, well, yeah, ice is also a mineral when it's the solid form of water. Sulfites have galena, sphalerite, pyrite, chalcopyrite, and cinnabar, and these are the ores of mercury, copper. This is iron and zinc and lead. Okay. Sulfates are gypsum and anhydrite, which go into plaster, and barite is a drilling mud. So with that sheet structure, it is very slippery and wet, and it's really good as a lubricant when drilling water wells, etc. Native elements are gold, copper, diamond, sulfur, graphite, silver, and platinum. Okay. The carbonates are primary constituents in limestone and dolostone. Calcite and dolomite are the two most important carbonate minerals. Many non-silicate minerals have economic value. For example, hematite is oxide mined for iron ore, halite mined for salt, sphalerite, sulfide mined for zinc ore, and native copper, which is mined for copper. Halite and gypsum are found in sedimentary rocks. Many have economic value. Here's just a picture of fluorite showing its 4 planes of cleavage as octahedral shaped crystal. Mineral resources are occurrences of useful minerals that will eventually be extracted, or deposits or concentrations of metallic minerals that can be mined at a profit. Economic factors may change and influence a resource. So a resource that may be too expensive one day to mine. When that mineral resource becomes more valuable, then it becomes affordable to mine it at a profit. Example of magnetite and hematite. Sometimes hematite's red, sometimes it's black. And if it's black, it'll look just like magnetite. So we can tell a difference. One by streak, so have a reddish-brown streak, magnetite with black streak, but magnetite's also magnetic, and they are both iron oxides. Here's a picture in a salt mine.